the diagram of a simple BJT circuit in which we know this BJT whether NPN or PNP based on the arrow indicated in this circle diagram. And the collector, for common collector, we can see that the collector terminal is grounded and set as a common terminal. Okay, for both input and output of a transistor. So in this configuration, the input signal is applied between the base collector region here and the output, which is taken from the emitter collector region. So the input supply voltage between base and collector, which is called as a VBC, while the output voltage between emitter and collector is labeled as VEC. Okay. And then for the input, the current input, which is we also know that the input will involve with IB, which is a current at base, and the output current, which is referred to the IE, which is I for the emitter. And if this circuit is considered as the common collector amplifier, it will have high input impedance and low output impedance based on the modulation between current IB and IE. And we can also calculate the voltage gain for this circuit. So let's us see the formula. Okay, so this one is input, and then this one is output. Oops. Okay, so and the formula for the current gain, which is can be referred as the AI current gain, which is we can get obtain from the ratio between the output current over the input current. So we can express this ratio as this equation, which is AI equal to IB over IE over IB. And then after you substitute IE equal to IC plus IB, you will get AI equal to IC over IB plus 1. And then we know that beta equals to IC over IB. And then finally, you can calculate current gain AI equal to beta plus 1. So this is also can be asked as a derivation part for the current gain for all BJT. And why? Because IE equals to IC plus IB can be applied to all type of BJT, whether PNP or NPN, whether common collector, whether emitter collector or base common base, common emitter or common collector. So for common collector, the input characteristic of the common collector configuration is drawn between collector base, okay, here, and also collector base voltage, which is VCB here, and also we can include base current, which is for the y-axis at a constant, emitter current voltage VCE. So we can notice that the input voltage VBC or VCB is largely determined by the VCE. So we have a different value of VCE here. So it depends, this curve, which is IB versus VCB, will be determined by the value of VCE applies to the BJT. So VCE we can calculate as VBE plus VCB. Okay, so this one is from the previous lecture. And then we rearrange this equation, and then VBE, I think you should know the value is for silicon is 0.7 volt, and then VCE you can calculate between the collector and emitter, and deduct with VCB, which is a collector and base. So for a right figure is output characteristic. Okay, so the output characteristic for a common collector, we can draw this output characteristic between IE and VC at a particular value of IB. Okay, so you can see the difference between input and output, and it depends on the type of BJT configuration. So if the input current is zero, okay, so the input current is zero, so we can see that the VCE also zero, and then you can notice there is a saturation region. Okay, and if the IE increases with controlled by the IB, so we can see if IB increases, the IE value also increase, but you should notice there is a saturation region, because both input and output loop is in forward bias, so there are a lot of charges or carrier there, and that's why they have a lot of charge carrier during this region, which is we call it as saturation region. So after a particular point, okay, with the increase of IB, there is a forward active region here before they reach to the breakdown part. Here is not shown in this diagram. And then below the IB equals to 0, there is a small region here which is indicated to the cut-off region. That's mean BJT is not working at all. Okay. So that's mean we control the value of IB to control the output characteristic graph. Okay. So for common emitter configuration, so in this configuration, we use emitter here. Okay, emitter as common terminal for both input and also output loops. So what does it mean by common? Means that this terminal as a reference, because we need to we have one loop, so that's mean they have bigger potential, higher potential and lower potential. So the potential difference between these two terminal will be indicated as input potential difference. Okay, So that's mean VBE with VE for the terminal for input, loop for the input. So for input loop, um, we can again, before that, again, the relation between the base, emitter, and collector currents can be written as IE equals to IC plus IB. Okay. So we can have two voltages here, which is VBE and also VCE, which is applied respectively to the base and the collector with respect to common emitter. So typically VCE should be bigger than VBE. So that's mean the BE here, input loop, will be in forward bias, while the CB here, which is the CBJ junction, CBJ, which is will be reverse bias. Okay, so the input loop, we know the V in and the V out here for the output, and V in equals to IB for the resistance. If the resistance appear here, which is IB plus VBE, and for the output loop, we can have VCC equals to ICRC plus VCE. And for power, we use common equation, which is P equals to VI. And for the output, the power for the output loop, definitely VCE times with IC. Okay, so normally we consider the output loop. Okay, so for common emitter here, which is the current still main flow based on the principle of IE equals to IC plus IB, and the base is the input terminal, and the collector would be output terminal. And then we can have that the base will control the collector current here. Okay, so the first loop, which is input loop, which is we have KVL, Kelvin law. Sorry, Kirchhoff voltage law, which is at a BE, we can get IB equals to VBB minus VB on over RB. So VB on is 0.7 volt for the silicon, and VVB is the source, and then you will get the value of IB that across for, of this resistor. Okay, so the next part is input characteristic for common emitter. So this is the how the the look of input characteristic, which is we will measure it between IB and VBE base emitter, and from the x axis and y axis, you can have delta IB for the y axis and delta VBE for the x axis. And then for base emitter, they will start to conduct, because VBE on, which is I mentioned just now, is 0.7 volts. So once they pass this voltage, around this region, so collector start to receive the current, and then we can calculate IC equals to beta IB. So beta, I think we already know from the previous lecture. So it will normally be, is an number which is start from 1 to 100 or 200 value, solid value. And then IB, we can calculate from the input loop, as well as from the input loop, and then you can get this. equation. So this is and then from the diagram here we can calculate the from the Kelvin Kirchhoff voltage law. Okay, so I think you should know that I'm referring to the output circuit, which is we have VCC minus ICRC equals to VCE. Okay, so and then you rearrange this equation, and then you will get negative VCE times with 1 over RC plus VCC over RC. So from the output loop, we can calculate IC value, and also we can and after that we can also calculate using this equation if we know the value of IB. Okay, so if we don't have we don't know how to calculate IB, that means we should use this equation. Okay, because this equation is very useful. Instead of calculate the value using a numerical method, you also can use this equation to calculate the value at using a graph, which is we call it as a load line. So let's say we have output characteristic for common emitter circuit is like this, which is we have a saturation region. Okay, so don't cross the line at the saturation region, because normally we will cross it at the active region, because we can see at what particular points of VCE or IC the BJT will function. Okay, so from this equation, active region. So I I take one, so IC, which is Y intercept at okay, then the line pass through Z at X or Y axis, we can see that will intercept with IC versus VCE. So we can notice the operating Q can be determined at here. Okay, so for y-axis, from the previous equation, we know that the intercept at y-axis equal to VCC over RC. So at this point here, okay, this is VCC over RC. Okay, so next point is VCC. So the VCC value is here, okay, at this particular point, and then So that's mean see that IC nearly constant and depends mostly on the IB. Okay, and then we can have a Q point here. Okay, so the intercept between the output characteristic, this is output characteristic with the load line of this BJT. Okay, I cannot approve this one. Mhm. Okay, and then the collector will collect only those free electrons that emitter inject the electrons to the base, and the number of these injected electrons will depends only on the IB IB circuit. Okay, sorry, base circuit. Okay, so now okay, we will see equation for the output circuit, which is collector and emitter loop of circuit with the same configuration. So VCE equals to VCC minus ICRC. So why? Because this one will refer to the Kelvin Kirchhoff voltage law, which is we should remove the load part. Okay, and at the same time, IC will be beta IB, and again PD, which is power equals to VCE IC, as I mentioned before, and then this is summary of transistor circuit approximations, which is the left side. Here is for the ideal. So that's mean ideal BJT, there will be a 0 volt for the base and emitter. Okay. So once you have to I mean if you set or if the question set they are using ideal BJT or PN junction ideal diode, so they will refer VBE equals to 0. That's mean um you have to deduct, you no need to deduct with a 0.7 volt for VBE. So that's mean IB we can get VBB, okay, the source over the resistor here, okay, for IB, and for IC we can calculate from the IB and beta DC. Okay, let's say in this circuit they gave the beta value is 100, and then for VCE, which is for the output loop, VCE equals to VCC minus ICRC, and then you will get this value. So now we look at the second approximation, which is we consider this one as a practical diode or practical PN junction. Okay, so when we use a practical type of junction, that's mean we need to consider VBE on as a 0.7 volt. Okay, and this one for silicon, if germanium definitely is 0.3 volt. So to calculate IB, okay, for ideal type, we no need to deduct or remove the contribution of VBE on. Okay, but for the practical one, we need to include this value, which is we want to get the resultant voltage across these resistor as, for example, 12 volt minus V, 0.7 volt for VBE on. And then you can see the value, even though in the same range, but the number or the value is different. Okay. And then next, once our IB value is different, that means our IC also would be different, which is you can see the change of the once the IC is different, how about now? Can you hear my voice? Oh, okay, okay. Uh, just now, connection actually. Okay, I will. Maybe I don't know whether I click exit meeting because there are a few student wants to join this meeting. Maybe accidentally. Okay, just now at which slide that stuck? Maybe I will resume. Start back at that slide. Can you hear my voice? Okay. Okay, now is it okay? Okay. So just now at which slide we stop? I mean you can't hear my voice. We explain. Is it this one? Which slide number can you common emitter circuit? This one. Is it slide 6? This one? Is it this one? Cannot see. Here. Can you see my slide? SRF 190045. Can you see my slide? Oh, cannot see anything. Okay. Okay. Now my voice, is it lagging, or I mean still lagging, or you can clearly hear my voice? Okay. So now okay, this slide is about load line analysis for common emitter circuit. Okay. The load lines analysis we can perform from have IC, from the output circuit, which is here. Okay, when we have IC equals to negative VCE times with 1 over RC plus VCC RC. So here we just compare with Y equal to MX plus C, and then you can see for the output circuit, which part is Y, which part of the equation is X. Okay, and C we can have very clearly which is VCC over RC. So let's say we have output circuit like this, lagging. Hmm. Hey, no, Ang, Angson, can you hear my voice? Now okay, ready kan? Okay. Maybe my line pun still raya. Okay. But I hope the line will be good to me for this 1 hour plus. Okay. So this one is okay. So lupa dah. Okay. Y equal to mx plus c, and c equation is VCC equal to VCC over RC, which is we can mark it on the y-axis for the output characteristic curve. Okay, so output characteristic curve, that's mean at the for the loop of CE. Okay, collector and emitter. Okay, so here I see at VCE equals to 0, we will get VCC over RC. Okay, and then for the x-axis, we can get the value of VCC. So here, the yellow line is load line. Okay, so we have this point, and then we have another point here. So once we join these 2 points, we will get a yellow line. Okay, but you have to make sure that load line should, I mean the line, the intercept of output characteristic, which is blue line and yellow line, load lines, which is, do not overlap at the saturation region, because it's not possible for the BJT to operate during the saturation region, because both loop would be forward bias. Okay, both loops will be forward bias. Then the yellow, okay, once yellow line and blue line cross, there will be one point here. So the cross point, the cross lines between blue and yellow at this particular point is called Q point. Okay, Q point is the operating point. So that's mean at start at this point above, the BJT will function very, 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 very well. Okay, and this Q point is depends on IB value, because IB value is a constant here. So as I show you before, which is for the IC versus VCE, they will have different IB value. Okay, the curve will be increased and the saturation region will be bigger. Okay, because you pump in because we know that a base will allow the charge carrier from emitter to be injected to collector, right? Okay, so the higher value of IB will increase or will widen up the region for the saturation. Okay, so this one is just to remind you, recall back about the CE of the equation for the CE loop, which is we have VCE equals to VCC minus ICRC. Okay, this one just follow the Kirchhoff voltage law. Okay, so total voltage in equals to equal to total voltage out. Okay, and again IC in forward active, we will get beta IB, and power dissipation is applies to all configuration, which is P VI. Okay, P equal to VI, and definitely which type of, I mean, which value of V. So because we consider the output loop, that's mean for this configuration we will consider VCE. Okay, and IC. So if you refer to the output characteristic, we have IC versus VCE. So don't take other current or voltage value. Okay, and then this one is a summary or comparison between ideal and practical. So what type of approximation we use to solve problems related to the ideal diode or BJT, or practical one, which is we call it as a second approximation method. So oh, what happened when both junction are forward bias? Okay, so if I have discussed in last week lecture, when both are forward bias, which is CBJ and EBJ, okay, there are a lot of current, charge carrier present in both loop. Okay, when there are two crowd of charge carrier, okay, that's why the current of collector will be sharply increased, even though you change a very small value of VCE. Okay, because too many of charge carrier, and at the same time you should aware that base is very thin, the thinnest layer among three layers. So whatever you pump in, I mean the what the charge carrier present in both circuit, it will, create chaos. I mean, not a chaos. It's something like too many charge carrier, and then it will tends to create the saturation area. Okay, so come back to this slide, which is transistor circuit approximation. Okay, so for ideal one, we know when we use ideal BJT or diode, the curve or IV curve is perfect, lies on X and Y. So the same thing for BJT because they use the same concept, which is PN junction. So when VBE for ideal is zero, okay, so we can see the effect of this value to our calculation for IB, IC, and VCE. Okay, so because if you use ideal diode or PN junction, so the total voltage from the source will be solely, 100% delivered to the resistor and goes into the loop. Okay, but okay, and then the value to calculate, the formula, we use the simple formula to calculate IB based on the loops, okay, which is a VBB over RB, and there is no other influence or factor control this VBB, and then you can use solely the value of VBB, which is the value you get is this one. But when you use practical PN junction or diode, you will have contribution of um, the material, which is the potential barrier, or what we call it as a VBE on. Okay, so for example, in this slide is 0.7 volt, which is indicate that this sample of, the PN junction will be is made up from the semiconductor type, silicon type. Okay, then we need to consider this value. Even though the value is less than 1 volt, but you can see the difference between the calculated IB value for these two types of BJT here. Okay, so because for ideal diode, we can strictly use the total voltage supply, but for the practical one, we have to consider the VBE on, and then the value for IB is different. So once the value of the value, because Sorry, I think my internet connection is not so good. Hmm. Okay, I try one more time. Maybe my neighbor still on holiday. Then I don't know. I will check whether someone curi my Wi-Fi or what. Okay. So okay. Uh this one okay, lagging. Okay. This one is it okay? This slide transistor circuit approximation, is it lagging? I mean, starting from this slide, right? Or this slide? Okay. At the end of that slide only. Okay. Okay, I will continue. I will continue. Is it clear my voice? Because just now I try with other laptop. Mm, okay. Okay. Now we will use a calculation method to identify whether the transistor, falls in what region. Because from the output characteristic, we can we can identify clearly a region for saturation based on the behavior or the trend of current versus voltage. Okay, so other approach, we can determine or recognize the transistor behavior using calculation. Okay, so let's start with a simple diagram here, which is we have IB, we have the source VBB, which is 4 volt. Okay, and also the value of resistance is indicate in this circuit. Okay, so okay, let's say we start with number one, which is the value of VE. Okay, VE is we want to know what is the voltage at the V, at the V, the emitter voltage VE. Okay, so VE we get 4 minus with a VBE, and then this is practical one because it's not indicated or it's not mentioned in the question where is the ideal one. Okay, so we should consider the VBE on, and then the second one is IE, the current flow to this circuit. We can calculate from the VE minus 0 because IE. Okay, and then over the RE, which is resistance at the particular emitter terminal. Okay, and then we can also calculate IC. Okay, so which is beta IB. Okay, because we don't have IB here, so we look at the alternative, which is IC equals to alpha IE, and alpha equals to beta over beta plus 1. Okay, so we because we only have beta, Okay, but we don't have IB. So you can use other alternative to calculate IC. Okay, so VC, we can calculate from this part. Okay, and then 10 minus ICRC, and then you will get 5.3 volt. And IE, because from this diagram, okay, so once you calculate IB, you can calculate IC. So once you have IC and IB, you can have IE, right? Okay, so then you can calculate IB using the equation, or you can calculate IE equals to IB plus IC. Okay, so okay, then how can we know whether it's active or not? So we must see, or we must look the value of IC and also VCE. Okay, but here we don't know how to calculate the VCE, right? Okay, so we should and also here we cannot determine. Okay, we cannot determine whether I saturation, sorry, VCE saturation, for example, because it's not given. Okay, so but you only can calculate the value of at each point, or terminal or element from here. But from this one, we know that IC and IB is bigger than 0. So bigger than 0, that means it's not in cut off. Okay, so now whether it's saturation or active. Okay, so again, we can see here, which is I give you as another example. It's quite actually it's almost similar to that one, but in real figure, which is we want to calculate I base. Okay, base current, and then we want to calculate the voltage across the resistor at the base here. And then if the beta is given as 200, what is the collector current? Okay, so here we know that 0.7 volt for the non-ideal BJT. So voltage across the base resistor from here, we can have a VBB minus a VBE, which is here given as 2 volt, and then we will get the base through the voltage, which is we already know the voltage IB. So IB, you use V equals this loop, which is VBB minus VB, have 13 microampere from this diagram. From this equation. Okay, so now the value of IB, you just plug in the value, and that's milliampere. Okay, is it? Actually, it's very simple calculation for BJT. So, but you have to familiar how to play with the formula. Okay, so to get familiar familiarized with the formula, you know the selok belok of the equation. So you know how to find the alternative, because the equation is there, but how to use the equation. Okay, so next example, we have this simple, also very simple actually. BJT for DC direct current, BJT very simple, not like AC. So because AC involved with tedious to me. Okay. But for this course, we only cover until DC. Okay. So the weakness of to get the value, to calculate, let's say the value of IE is not given, and they don't know which equation they should use. Okay. So here we have VBB, which is given as 4 volt, and then RB at the input loop as 22 kilo ohm, 220 kilo ohm, and also RC, and we stated that VBE on as 0.7 volt with a value of 200. Okay, this one is input, and then this one is output circuit, and then you can calculate. Um, I just want to show the variety. Many approaches that you can use to calculate uh, base current, collector current, or emitter. Whether you can start with the voltage of resistor, or you can depends on the parameter given in the question. Okay, so this one we can straight away calculate IB using Ohm's law, and then you will get 15 microampere, and then you can calculate the collector. Okay, and then plug in the value of beta, which is 200, and then you get diagram. And lastly, you can calculate the IE. Okay, so as given in this question, and also you can calculate the voltage of circuit, which is collector CE. Okay, so CE voltage, which is output, and this one as discussed before, which is VCE equals to VCC minus ICRC. Okay, and then you just plug in, substitute the values given in this diagram or in the circuit, and then you will get 4 volt. Okay, the same thing for this question. Just one. Okay, but the tricky part is only alpha given for this question. Okay, so alternative for IC, you can have alpha IE, but before you get IC, that means you should get IE. Okay, so IE you can get from the BE loops, which is input loop here. Okay, and then you will get a value of IE equal to 1 milliampere. Okay, another mistake that commonly done by student is the unit. Okay, if micro, milli, okay, or kilo. So be careful. Okay, I don't know, but last semester I think 30 or 40% student did mistake in unit writing. In unit. Okay, and again the same concept we apply for the CE loop, which is as discussed in the previous slide. Okay, this one is another part. Okay, but we can manipulate the question by putting, for example, another condition. In this example, we can mention, or put the condition when VEC is 0.5 of VCC. Okay, So you no need to worry because normally the question will be, I mean, the value of important parameter will be given in the text or in the diagram, or both. Okay, so parameter values given in the text in the question. Okay, for example, here we change a little bit that we EB on is 0.64. Oh, doctor, why now become VEB, not VBE? Okay, why? Okay, MP or MPN, something like that. Okay, so this one is for PNP. If the direction of arrow out of the circle, that's mean NPN. Okay, FEP. Because it depends on the type of BJT. Okay, but the concept of calculation is the same. Okay, you will use IC equals to beta IB. You need to use IE equals to one plus beta IB to calculate the IE. Okay, and also the IB will so you need to get the potential over the resistor. So but you have to check whether which part is input and which part is output. Okay, and then for this question you need to put in consider the VC equals to 0.5 VCC, and then you just get it from the above calculated value, and then plug in to get okay, is NPN BJT because the arrow is out of the circle. Okay, going up. Yes, I play with the construction of BJT. Okay, because I don't want you to stick to one. Don't to be loyal in this part. Okay, with the NPN or PNP. Yeah. Okay. So, but the concept of emitter current would be the same, which is this equation, three equation is applies to all of the NPN or PNP for both, okay, which is IE equals to IC plus IB, and also IC equals to beta IB, and also IB you get from this diagram or from the input circuit to calculate the IB, which is from the Ohm's law, potential difference over the resistor at the base to calculate the I base. Okay, so now how to recognize the BJT operation by calculation. Okay, okay, everyone can see this slide. This slide is summary of to calculation numerical method. Okay, just now for cut off function, that's mean current for the base is 0, current for the collector also 0, and VBE should be lower than 0.7 volt because the carrier cannot cross the base. Okay, so that's mean once you calculate the IB, for example, VBB minus VBE on over RB, you will get IB equals to 0. So definitely you will know that BJT is in cut-off region. Okay, because once IB equals to 0, IC also 0, right? So IC equals to beta IB. So definitely will be 0. So definitely you already know that, oh, that is cut off. Okay, but for saturation and forward active, IB is bigger, I mean higher than 0, bigger than 0. Once we get IB, definitely we can calculate IC. Okay, so there is a similarity between saturation and forward active, in which the value of IB and IC equals to 0 here. Okay, so that's mean when there is a IB value, that's mean the VBE is equal to 0.7, or in other words, the charge carrier already, I mean, able to overcome this potential barrier to be which is a VBE on. Okay, this is another um, similarity between saturation and forward active. Okay, but for saturation, okay, we can have that for the output IV curve, the VCE is low. Okay, normally is below than 0.2 volt. Okay, once we change the IB at the different values. And then for the forward active, we can see that VCE is smaller than VCC. Okay, so that means VCC is the voltage supply at the collector. Okay, and here we can calculate this one. You already know that IC can be calculated from beta IB, and here VCE, okay, at the output loop is bigger than VCE saturation. So how do we know the value of VCE saturation? So normally in the question it was stated the VCE saturation is what value will be given in the question. Okay. So that's mean in saturation region, VCE saturation, that's mean VCE is lower than VCE saturation, because it will fall in this, where is it, in this region here, here. Okay, so that's mean VCE should be lower than VCE saturation. Okay, that's why we will get the hmm, is it hilang pula. So okay, we proceed with a simple example, which is in this circuit we have a VCC, and then beta equal to 100, and stated there VCE saturation is 0.7 volt. So to identify whether the BJT is forward or reverse, we will depends on this, which is VCE will be bigger than 0.1 volt. Okay, so in other words, you have to calculate IB, uh, then you calculate IC, and then you calculate PCE, right? Because these three factor will indicate which region this BJT are located. Okay, so for this first set of question, which is we set VBB equal to 1 volt. Okay, so Again, we can use Ohm's law, which is IB equal to VBB. Okay, VBB is the source of the base. And then we have VB on, which is 0.7 volt. And then we have RB, which is 12 K ohm. And then you just plug in and then you calculate the value, you will get 2.5 10 power of negative 5 ampere. So that is value of VB of IB. Okay, so that's mean base emitter loop is in the input loop. Okay, so next part, we already know IB. We want to know, because I already mentioned that once IB have value, that means IC also have value. So we should know what is the value of IC. So IC is beta IB. Beta is given as 100, and then you substitute the value of IB, which is calculated from the Ohm's law using input loop, and then you will get 2.5 ampere. Okay, so the next part is we want to, because we want to identify each condition. That's mean we need to know the VCE. So VCE we can calculate from the output loop, which is a collector and emitter loop. And then we have VCC minus ICRC. And then this one VCC is given as 12. And then we have IC from this part, which is 2.5 10 power of negative 3 ampere. And then RC is given as 2. Oh, this one is not 12. This one is 2. Okay, it's not 12. 2 power of 3. Okay, I make should be not. Okay, so and when you calculate, I think you will get a 7 volt. Okay, here. So if you see from here, 7 volt is bigger than V saturation. VCE saturation. That means we can consider that this BJT is inactive region. Okay, let's say you calculate VCE and then you get 0.05 volt. That means it is saturation region. Okay. So in other case, let's say if you calculate IB equals to 0, that means IC equals to 0, that means it's cut off. So only 3 condition you can consider here, which is a cut-off, active, and also saturation. So that is how we determine the condition of operation region of BGT. Okay, so that's all for today. Any question?